Welcome to this explainer. Okay, today we are taking on a massive, century-old physics mystery. It's a puzzle that literally changed how we view reality, yet it left one of the absolute greatest scientific minds in human history deeply, deeply frustrated. We're going to explore a centennial reappraisal of quantum mechanics and see if we can finally, piece together the logic behind the universe's most bizarre rulebook. Let's dive in. The theory says a lot, but does not really bring us any closer to the secret of the old one. That is a direct quote from Albert Einstein, and he was complaining about early quantum mechanics. See, while the math worked perfectly to predict experiments, to Einstein it felt, well, entirely arbitrary. It lacked a foundational logic. This deep frustration really established the incredibly high stakes of what became known as his quantum riddle. So what exactly is the quantum riddle? It essentially boils down to this. What are the principal reasons behind the existence of the quanta? Einstein didn't just want a how-to manual on calculating atomic energy states. No, he wanted to know why the universe was forcing us to use these strange, disjointed quantum rules in the very first place. Basically, he wanted to peek under the hood of reality and understand the machinery. Section 1. Heisenberg's magical math, changing the rules of the game. To find our first real clue, we have to examine a massive foundational leap made by a young Werner Heisenberg. And to ground this incredibly dense theory in real human history, let's just walk through the timeline for a second. In July of 1925, a 23-year-old Heisenberg publishes his breakthrough Helgoland paper. He essentially creates matrix mechanics. Then, boom, within a single year, 1926, Paul Dirac formalizes this framework using his now famous bracket notation. Fast forward to 1928, and physicists like Hermann Weyl, Pascual Jordan, and Eugene Wigner are rapidly expanding on these rules. I mean, this was a frantic, lightning-fast period of discovery that literally laid the bedrock for all of modern physics. But here's the truly wild part about that discovery. Decades later, legendary Nobel-winning giants like Enrico Fermi and Steven Weinberg still described Heisenberg's sudden mathematical assumptions as incomprehensible and magical. Heisenberg basically guessed the correct mathematical structure without any rigorous philosophical foundation for why he was doing it. He just kind of knew it worked. Okay, let's dive into this and compare exactly what he did. In the classical math of our everyday world, equations are commutative, right? The order doesn't matter. 3 times 4 is the exact same as 4 times 3. But Heisenberg comes along and proposes this radical new quantum math, a non-commutative kinematics, where the order of operations suddenly matters immensely. Position times momentum minus momentum times position does not equal 0. Instead, it equals a fundamental constant involving imaginary numbers and Planck's constant. He quite literally changed the fundamental rules of multiplication. Section 2. Restoring quantum equilibrium, the missing clue. Right, so we need to introduce the missing clue in our century-old detective story. And to understand it, we actually have to look back to classical French mechanics, specifically D'Alembert's principle. Now, this is a foundational law stating that dynamical motion is an equilibrium condition once the force of inertia is incorporated. Simply put, it's about perfectly balancing the forces of inertia against external forces. But here's the kicker. For over a century, this deep classical equilibrium connection to quantum mechanics was rarely even explored. And this brilliant principle perfectly illustrates what Heisenberg was intuitively doing. He kept Newton's laws intact, but to maintain that deep, hidden D'Alembert equilibrium down in the atomic realm, he had to change the kinematic variables. By placing mathematical hats on classical quantities, standard numbers transform into operators. His bold hypothesis was essentially that classical equilibrium is restored in the quantum world, but only, and I mean only, if we use these strange non-commuting operator objects. Section 3. Completing the rulebook, filling the logical gaps. Now, what's really interesting about this is how other brilliant minds attempted to complete the rulebook that Heisenberg started, because it actually took decades to fill in the logical gaps. Paul Dirac formalized Heisenberg's math by connecting it to classical equations known as Poisson brackets. But there was a missing link, the Lagrange bracket. Reintroducing this completely forgotten piece of classical mechanics finally provided a direct, solid theoretical foundation for how particles of matter operate. It effectively ended a near-century-old puzzle about the inner workings of subatomic fields.
And completing this logical framework reveals a truly fascinating mathematical split. On one side, we get commutators for bosons, your particles of force, like photons. But on the other side, once we introduce those forgotten Lagrange brackets, we perfectly derive anti-commutators for fermions, the particles of matter, like electrons. It proves without a doubt that the universe requires two distinct, mathematically balanced rulebooks. And for the first time, we can finally prove exactly where they both come from.
Section 4. A cosmic quantum twist. Zooming out to the universe. Okay, so we've spent this entire time looking down at microscopic particles, right? Well, now let's pivot dramatically to the macroscopic universe. Because to make all this quantum math perfectly consistent, modern analysis reveals the absolute necessity of an underlying mathematical constraint. Think of it as a hidden function literally forcing our universe to play by quantum rules. The source text playfully dubs this hypothetical constraint the red October function, and it's represented by the letter F. It just sits there, beneath the surface, quietly dictating algebraic consistency. But wait, when we break down the variables inside this function, things get truly mind-bending. The hidden constants inside this tiny quantum constraint might perfectly map onto the largest mysteries of cosmology. Let me explain. Constant A represents a background velocity, so could this be the expansion of the universe? Constant A prime acts as background acceleration, perhaps that accelerated expansion we attribute to dark energy. And constant B acts as particle mass renormalization, strongly hinting at Mach's principle. Researchers are even suggesting we could hunt for the signatures of these massive cosmic variables using modern quantum dot experiments. How cool is that?
Which brings us to an ultimate, absolute drop-the-mic question. Could microscopic quantum rules explain the expanding universe and dark matter? Take a second to really think about what this means. Heisenberg's seemingly random, quote-unquote, magical mathematical leap back in 1925 might be directly tied to the fundamental constraints governing the expansion of the entire cosmos. The mathematics of the extraordinarily small are directly dictating the shape of the extraordinarily large.
So we conclude today by bringing our story full circle, right back to Einstein. Subtle is the Lord, but malicious he is not. If this centennial reappraisal is correct, the underlying rules of reality aren't just some arbitrary malicious trick. No, they are part of a deeply interconnected equilibrium, tying the tiniest particle directly to the expanding fabric of the cosmos. As we head into the next 100 years of quantum mechanics, we really have to ask ourselves, if the secret to the entire cosmos was hiding inside a single atom this whole time, what other universe-shattering truths are just waiting to be uncovered?